Okay. So, this is but remember this is a linear analysis, and linear analysis is strictly not correct for doing for oscillators, we have already discussed, but it tells you what is the condition for this oscillation to start. And once the oscillation go on building up, then of course non-linearity to come into picture and stabilizes the amplitude to some specified value depending upon the non-linearity built into this amplifier here. So, at this level of the course, we normally do not go beyond this analysis. In fact, most electronics courses do not touch upon how it behaves under the final steady state condition. This only gives you the condition for oscillation. Okay. So, this is simplified picture of this, I mean not simplified, I mean simplest oscillator, which is the Wien-Bridge oscillator. How do we get these three? Remember your operational amplifier, you want a non-inverting gain of 3. So, you take a amplifier, operational amplifier and put the input here and then provide feedback, right, and this is 2R and R, some other value. Then the gain of this amplifier is equal to 3. So, this box, you plug it in here. So, this is how you make using an operational amplifier a simple Wien-Bridge oscillator, which you will do in the laboratory in the next experiment. This is a Wien-Bridge oscillator. The other oscillator is a bit more complicated oscillator in terms of calculation, not conceptually. Requires a lot more calculation, that is all. What people thought is that if I have one stage RC network like this, then what is the transfer function of this? Will be output voltage will be equal to this divided by the two impedances, right. So, it has some amplitude wave function which will be like this at S is equal to 0, no, I am sorry. At S is equal to 0 is open, so there is nothing transferred from here to here. At S is equal to infinity is a short circuit, so it becomes equal to 1. So, this is how this variation is in terms of the magnitude. What about a phase? Phase will start at pi by 2 because of the capacitor here, and then it goes to 0 as omega goes to infinity. So, this network can at most provide a phase shift of maximum value equal to 90 degrees. Okay. So, if you put two such networks, hopefully you get 180 degrees phase shift, provided you are operating at this frequency, 0 frequency. If you go slightly more frequency, this is no longer a pi by 2. So, if you put two of them in cascade, the phase shift you will get will not be 180 degrees, right. So, to really get 180 degrees phase shift, you will have to operate it somewhere here, but one section will not do, you need to have more than 2 sections. So, people have chosen 3 sections like this in cascade, so that overall phase shift obtained by the beta network is equal to 180 degrees. Then amplifier provided the remaining 180 degrees, so that the loop gain is equal to 1, right. Loop gain must have angle 0. So, the total angle which is 360 degrees obtained 180 degrees from the three cascaded section of this, and the amplifier provided a 180 degrees by a minus in the amplifier A. So, overall phase shift is equal to 360 degrees. So, this was the viewpoint on which the phase shift oscillator was designed by using this concept of phase shift. That is why the name phase shift. And then initially they made some mistake of putting them like this, and this you can see is does not give you correct result because the loading of one on the other. So, ideally if you could isolate these by putting a unity gain amplifiers, are you with me? So that this section is isolated from this section, this section is isolated from this section, and this is the ideal unity gain amplifier. So that the input impedance is infinity and output impedance is equal to 0. So there is no loading of one network on the other. So people made such an oscillator once upon a time, and this is called the ring oscillator. Using three isolating elements here, but this is a very expensive proposition to put three active devices in between, three active circuits in between, which are the unity gain amplifiers. So people said, let us remove those and then see what happens. So that resulted in the final version of the phase shift oscillator. Still RC, where you have an amplifier negative is other terminal is grounded. Although it is not necessary to have all these resistors in same value, it is easier to make this all this value same. So the 180 degrees is obtained from this network and 180 is obtained from the amplifier here. So that the loop has a total phase shift of 360 degrees. So the condition of zero angle is satisfied. So A is obviously should be a inverting amplifier to get a minus sign there, and then this network provided the remaining 180 degrees. If you do a similar analysis, it is a bit longish to go on doing it here. You know how to analyze this, you don't know to do. I am sorry, I put the wrong direction. Now, if you analyze this circuit for A beta and equate it to 0, you get the following equation. where omega naught is equal to 1 by RC. This omega naught is the oscillation frequency, but I am just calling this 1 by RC as equal to omega naught.